Hi there. In this video, we're going to consider an additional example of how to write the Fourier series for different kinds of functions. So this is the function that we're considering. So we're saying that f of x takes on the value of minus x, that's y is equal to minus x, between minus pi and 0. And thereafter, it just takes on the value of 0 between x is equal to 0 and pi. And we will complete this by saying that it's a periodic function by taking on the value of f of x every 2 pi units. 2 pi is our period. So how do we go about writing the Fourier series for this? Well, we have to determine our Fourier constants. And the first one that we do is a naught. A naught is equal to 1 over pi multiplied by the integral from minus pi to pi of simply f of x dx. So this is equal to 1 over pi, and then we simply substitute f of x, so that's minus x, between minus pi and 0, and of course 0 after that, so there will not be any term. So let's substitute that in. So from minus pi to 0, we have minus x dx, and then we have from 0 to pi, 0. So the integral of minus x is just minus x squared over 2. That's integrated from minus pi to 0. So if we substitute in 0, we get 0, and then minus and a minus would give us a positive. So we're left with pi squared over 2. So 1 over pi multiplied by pi squared over 2. So this gives us just pi over 2. So that's what a naught is equal to. So next we determine an and bn. So an, if we remember, is the integral from minus pi to pi. There's also a 1 over pi in front. And it was f of x times cos of nx. So we do our substitutions. So we get 1 over pi, and we have the integral from minus pi to 0, and that was minus x. So we have minus x cos nx dx, and then plus 0, the integral of 0. So this integral is obviously going to give us 0. So we need to evaluate x cos nx. So we have two functions that are being multiplied. So we have to use integration by parts. So let's just remember what that is. So how we would do it is we would say it's the product of two functions u and dv. And that's equal to uv minus the integral of v du. So we essentially choose one function to differentiate and one function to integrate. So the function that we're going to differentiate is x. So that's what u is. So we'll say that u is equal to x. That means that du is equal to dx. And what we're going to differentiate is dv. So we'll say that dv is equal to cos nx dx. So dv is equal to cos nx dx. And if we integrate this, then we see that v is simply equal to sine nx divided by n. So what we now need to do is substitute these things in. So we have uv, therefore we'll have x times sine nx over n. So as I've just stated now, the first term is uv, so that will be x sine nx divided by n. And also recall that this is a definite integral that we're considering, so it's uv, but we have to integrate this as well. So what we're going to do is also swap the order of integration. So the minus pi and the 0, we're just going to swap that around just to make it a bit easier. So we're going to have 0 to minus pi. And since we have done that, we have removed this negative. So the next term is a minus. And now we have the integral, so we're going to do the same thing. We're going to reverse this order of integration. So we're going to have from 0 to minus pi. And then it's v du. So v is sine nx over n, and then du is just dx. So we're going to have sine nx over n dx. So now we can evaluate this. So sine of minus pi is just 0, so that's not going to do anything. And then sine of 0 is also 0 as well. So now here, so what's going to happen is that we're going to integrate sine nx, okay? So the integral of sine is minus cos, so that's what we're going to put in. And remember that cos of minus x is just the same thing as cos of x, so we need this. So long story short is that it's going to become plus. So we're going to have cos nx divided by n squared from 0 to minus pi. So when we put in cos of minus pi, this is where we're now going to use our trig identity. So let's just write that again. So cos of minus x is equal to cos of x. So when we put in minus pi, all that we're going to do is we're just going to get cos of pi. So we have 1 over pi into cos nx, sorry, cos n pi divided by n squared, and then minus 1 over n squared, because the cos of 0 is 1. So we'll just have 1 over n squared. So if we were to simplify this, when we pull out n squared as a common factor, what we get is 1 over pi n squared into cos of n pi minus 1. So this is what an is equal to. So now we just have to understand how we will actually substitute this in the Fourier series. So the easiest way to do this is to just do it for even numbers and for odd numbers and all of these things. So let's just remember what cos looks like. That is the graph. So we have 1 and we have minus 1. and it starts off at 1 when x is equal to 0. So then it goes down to 0 when x is equal to pi over 2, and then it goes down to -1 at when x is equal to pi, and then it repeats itself like that. Okay, so that's pi over 2. That's pi. So this is 3 pi over 2. And that is 2 pi. And that is 5 pi over 2. And that is 3 pi. And so on. So let's have a look at even numbers. So even numbers would be n is equal to 2, 4, 6, etc. So if n is equal to 2, so we substitute 2. So it means cos of 2 pi. Cos of 2 pi is equal to 1. So 1 minus 1 is 0. Okay, so this entire term is 0. So it's the same thing now if we substitute 4. So if we have cos of 4 pi, we're going to get 1 again. So that's 4 pi here. There's 4 pi. So 1 minus 1 is 0. So we see that we get 0 for even numbers. So an is equal to 0 for even numbers. So now we try odd numbers. Let's say n is equal to 1, 3, 5, 7, etc. So if n is equal to 1, so we have cos of pi. So cos of pi is -1. So -1 is -2. So what we have here is -2 over pi n squared. So let's now check 3. So if we have 3, that's cos of 3 pi. Cos of 3 pi, so there's 3 pi here. Cos of 3 pi is -1. So again, that gives us -2. -1 is -2. And we have the same thing, -2 over pi n squared. So we can see that 1, 3, 5, etc. So for odd numbers, we have -2 over pi n squared. So for even numbers, it's equal to 0. And then for odd numbers, an is equal to -2 over pi n squared. So that is an. So we now repeat the same process for bn. We would remember that bn is equal to integral from -pi to pi f of x, but this time multiplied by sine nx. So all we do is just substitute that in. So we have 1 over pi. We integral from -pi to 0 of -x sine nx dx. And the remainder is from 0 to pi, and that value was 0. So that's not going to give us anything. So this is all we're integrating. And we use integration by parts in the same manner. So let's just write down that formula again. So we have u dv equal to uv minus the integral of v du. So we'll differentiate x and integrate sine nx. So that means that we'll set u to equal to x. That means that du is equal to dx. Then we'll set dv to be sine nx dx. And if we integrate that, we get that v is equal to minus cos nx divided by n. We can now substitute all of these things inside our equation and determine Bn. So we have 1 over pi and then uv, so u is equal to x and v is equal to minus cos nx. So it's minus x cos nx divided by n. And this is integrated from 0 to minus pi. So we have swapped around the order of integration as we had done with an. And then we're going to say plus. So there's a minus here and a minus here, so that will give us a plus. And we have the integral from 0 to minus pi, so we've just swapped that around again. And we have cos nx divided by n dx. So we can now evaluate this. So if we do that, we'll get 1 over pi again. We'll just keep this the same, so we'll just write it as it is once more. So we have minus x cos nx divided by n, integrated from 0 to minus pi. Then we have plus. Then the integral of cos is sine. So we're going to have sine nx divided by n squared from 0 to minus pi. So the integral of sine of minus pi or pi is just going to be 0. So this first term is going to give us 0. And sine of 0 is also 0. So there isn't going to be any term here. So now we can only evaluate this first term. So we have 1 over pi, and now we do our substitutions. We can substitute in a minus, and a minus is going to give us a plus. So we're going to have pi times cos n pi divided by n. And then we're going to have 0. So if we just substitute in 0 here, we're just going to get 0 because in place of x. So there isn't going to be any term there. So that pi and that pi is going to cancel out. So what we're left with is just cos nx over n. And now if we substitute in our different values of n, so if n is odd or n is even, so let's just say now that n is odd. So if n is odd, we're going to have cos of, sorry, this is a pi. We're going to have cos of pi, then cos of 3 pi, cos of 5 pi. And then if we look at our graph, so if we have odd numbers, there's 1, 3, etc., we're going to have minus 1. So for odd numbers, we're going to have minus 1. So if n is odd, then it means that Bn is equal to minus 1 over n. So now if n is even, then it means that Bn is now equal to 1 over n because we're going to have positive numbers. So that's easy to see as well. So there's it here. So 2 pi, 4 pi, etc. we see that it's equal to 1. So now we can substitute all of these things in our Fourier series. That means that f of x is equal to, so remember the general form of the Fourier series, it's a0 over 2 plus the sum, where n is equal to 1 to infinity, and we have an cos nx plus bn sine nx. So a0 was equal to pi over 2, I believe. We can just go up and see that. there was a naught, and it was pi over 2, and an was minus 2 over pi n squared, and that was for odd numbers only, and for even numbers we saw that it was equal to 0. And lastly, bn was minus 1 over n or 1 over n. So substituting all of these things, we have pi over 2 divided by 2, that gives us pi over 4. Then we have minus, so remember that it was minus 2 over pi n squared, so bring out the 2 over pi as a common factor, and then the remainder of the terms of n was 1 over n squared. So we have cos of x, so let's just remind ourselves, an was equal to minus 2 over pi n squared. This was for odd numbers, okay? So the 2 over pi, we took it out as a common factor in front. Now we have 1 over n squared. So cos of 1, if n is equal to 1, is just there. Then we have 3. Remember, we don't have any even numbers, so we'll ignore that. So we'll have 1 over 9. Then cos 3x. Then we have 5. So we have 1 over 25. Cos 5x. And so on. Then we have the sine terms. So n was 1 over n, minus 1 over n for odd numbers and 1 over n for even numbers. So we'll just say it's minus, so we'll just put the minus in front. And then what we'll do is that for every odd number within the bracket, we'll say it's a positive number. And then for every even number, it's a negative number. So we'll have sine x. So a minus and a minus will give us, a minus and a plus will give us a minus. So therefore, for odd numbers, we have negative, so that corresponds. So now for the first even number, we'll say minus, so a minus and a minus gives us a plus. That will correspond to the positive for the even number. So we have 1 over 2 times sine of 2x, and it carries on like that, 1 over 3. So every alternative coefficient, it will alternate between positive and negative. So we have plus 1 over 3 sine 3x, and so on. So this was the Fourier series for another example, and the only thing that we had to do differently from the previous example that we had done was that we had to use integration by parts to evaluate the integral involving x. So for this portion of the graph, we had x cos x and x sine x. And we had to use integration by parts to evaluate the Fourier series for these portions. But that was not very difficult, and we can see how we can calculate the coefficients anyway. So thank you very much for watching. In the upcoming videos, we will consider generalizing the Fourier series for any kind of period. Remember that these periods now are valid for 2 pi. So how would we write the Fourier series for any kind of period? So generalizing it, and how we would write the Fourier series for half-range series, and a few other considerations. So thank you.